Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 19, Organic Chemistry 2. Today we will continue on chapter 4, Aldehydes and Ketones, Nucleophilic Addition Reactions. Recall from the previous lecture that the reactions of aldehydes and ketones undergo nucleophilic addition in basic media, so the nucleophile will be negatively charged, attacks on the electrophilic carbonyl carbon, forming alkoxide. The alkoxide gets protonated from the media, and we get product, addition product. It's nucleophile and H. Nucleophilic addition under acidic condition. Weak nucleophiles such as water and alcohols can add to activated carbonyl groups under acidic conditions. فكربونيل اللون بير بتوع الأكسجين gets protonated first, and this species will be in resonance with carbon carrying positive charge. Then nucleophile will attack now on this electrophilic carbon, we'll call it activated form, to form the protonated product. Deprotonation furnish the final product. We have different types of nucleophiles. Let's assign them on the basis of the nucleophilic atom. So we have oxygen nucleophile like water, alcohol, diols, sulfur nucleophile, nitrogen nucleophiles, hydrogen nucleophiles like in hydrides, and carbon nucleophiles. We will take them one by one, oxygen and sulfur, in this lecture. The oxygen nucleophiles, hydrate formation, when we react the aldehydes and ketones with water, we get the hydrate structure. Again, base catalyze, so the OH minus will attack on the electrophilic carbon, forming the alkoxide, which gets protonated proton transfer to get the hydrates. In the acid-catalyzed, first protonate the double bond, the lone pair. We get this species, which then the water will attack on the carbon, forming this oxonium ion, proton transfer to get the hydrate structure. Acetal formation. Instead of using water, we use alcohol. So carbonyl compounds, aldehydes and ketones, with alcohol in catalytic amount of H+, like sulfuric acid or para-toluene sulfonic acid, we get acetal. First, the alcohol, some molecules of the alcohol will get protonated to form this species, and this species will work as a proton source. So the lone pair of the carbonyl will get protonated. That's the first step. Then another molecule of alcohol will attack on the carbon, forming exonium, proton transfer. This time we are forming hemiacetal. This is the carbonyl carbon. As you can see, it's carrying OR and carrying OH. We call this hemiacetal. The OH, the oxygen lone pair of the OH group, will attack and gets protonated. This lone pair on the OR will donate its electron, pushing the H2O as a leaving group out. For this reaction to go well, we have to get the H2O out of the reaction. So the reaction, the equilibrium will go forward to give you the product. So here we have O plus. This species, the carbon in the resonance structure will have the positive charge. Here the oxygen lone pair attack, forming this oxonium, hydrogen transfer to form acetal. The original carbonyl carbon, instead of carbon double bond oxygen, will carry 2 OR, 2 alkoxy group. Okay. Propose a mechanism for the acid-catalyzed hydrolysis of acetal. It is a reverse of the formation of the acetal. The acetal could be hydrolyzed easily using acidified water. So the first step will be the protonation of the oxygen of one of the OR group. Then the lone pair of the other one will kick this HOR group out. Then another water molecule will get in as a nucleophile, add to the C double bond O plus R, forming this oxonium ion. This proton will be transferred to a molecule of water, giving the hemiacetal intermediate. The second oxygen OR will get protonated. Then the oxygen lone pair of the OH will kick the ROH molecule out. Proton transfer to another molecule of water will lead to the formation of the starting carbonyl compound. Reaction of aldehydes and ketones with ethane 1-diol, common name ethylene glycol, in presence of catalytic amount of acid like sulfuric or paratoluene sulfonic acid, gives intermediate hemiacetal followed by intramolecular substitution reaction to give the cyclic acetal. So this oxygen will replace this oxygen to form the cyclic product. Show what alcohols and carbonyl compounds give the following derivatives. This carbon carries the 2 oxygen, so I will cut in here and transfer these two the carbonyl, and each one of these oxygen will have H, so we'll have two of that. For this is the carbon carrying the two oxygens, so I will cut in here. This carbon will be carbonyl, and this will take H, and this will take H. So this is a carbonyl, fine. This already I gave an H, OH, and here I put an H, so an OH, alcohol. Predict the product of each of the following reaction. Acetophenone with excess methanol, catalytic amount of sulfuric. This is a carbonyl, right? So we replace this double bond O with 2O methyl, and the product will be 1,1-dimethoxyethyl benzene. Here we have this carbonyl. This compound contains two OHs. They will replace the C double bond O and give spiral compound. Okay? This is a carbon. Stable hemiacetals and acetals. A very clear examples are saccharides. Monosaccharides present in open and cyclic form. So glucose, open structure, where the aldehyde functionality number 1, and we have OHs in this O lone pair attacks in here on this carbonyl to form a 6-member ring, stable cyclic hemiacetal. Lactose, glucose, galactose molecule obtained via 1,4-glycosidic link. In the glucose, this carbon is hemiacetal. In lactose, this carbon is acetal, has 2 OR on it. And this carbon is a hemiacetal carbon. Show how you would accomplish the following synthesis. You may use whatever additional reagent you need. We have here 3-oxohexane carbaldehyde. We have ketonic functionality. We have aldehydic functionality. We know that the aldehyde is more reactive than ketone. The product I would like to accomplish is 3-hydroxymethyl cyclohexane 1-on, where we reduce the aldehyde in presence of ketone. Well, we can select the mild reducing agent sodium triacetoxyborohydride, and we can achieve our target. Okay? Now, if you would like to do the other way around, reduce the ketone in presence of the aldehyde to get this compound. So we know that aldehyde is more reactive than ketone. So we react this with one equivalent ethylene glycol in presence of acid. The aldehyde will react to form the cyclic acetal. Then reduce the ketonic functionality with sodium boron hydride to get the hydroxy alcohol. hydrolyze the acetal back to aldehyde to get 3-hydroxycyclohexane carbaldehyde. Sulfur nucleophile. It's almost like the oxygen nucleophile from the same family. So reacting aldehyde and ketones with alkane thiol will provide thioacetal. If we have 1,2-dithiol, we will get again the cyclic acetal. When treated with raninakel, thioacetal undergo desulfurization, yielding alkane. So we have here thioacetal, raninakel, and hydrogen. We get the CH2, the alkane. So this is the third method we covered so far to transfer C double bond O to CH2. Before we have taken Clemmensen reduction, Wolff-Kishner reduction, and here we have to transfer the carbonyl to thioacetals, then desulfurization using raninakel hydrogen. Draw the structure of cyclic compound that is produced when acetone is treated with 1,3-propane dithiol in the presence of acid-catalyzed. Propan to on propan 1,3-dithiol. Of course, it will be the cyclic. Thioacetal to 2-dimethyl 1,3-dithiene. To shed light on the application of this chemistry, let's take this example. When we react aldehyde with 1,3-dithiol, we get this compound. The hydrogen here can react with N-butyllithium to form the organolithium. We react that, remember that this has partially positive. Now this carbon has a partially negative. Again, it's like en Bolong as we did in Grignard. Then this organolithium reacts with alkyl halide to form this compound. The protection of the sulfur using water and mercury chloride gets ketone, so we transfer here the aldehyde, replace it with R prime and obtain ketone. Or we make a reduction, desulfurization, and with raninakel and to get alkane. So this method is useful to transfer aldehydes to ketones or higher chain alkane. The deprotection mechanism, why we used water, mercury chloride or mercury oxide. The sulfur would like to form a very strong bond with mercury, so sulfur will, a lone pair, will attack on the mercury, kicking Cl out, form this species, then the lone pair of sulfur will form a double bond here, and this will be leaving group, so will be double bond. This carbon is electrophilic carbon, so it will be attacked by water molecule oxygen. Okay, forming this species once again sulfur lone pair, will attack on the mercury, getting Cl minus out, forming this species. Now these two electrons will move in the carbon-oxygen bond and kick this out. So we have to kick this species out as well as H plus to furnish the carbonyl compound back. See you next lecture. Bye bye.